Hello all. In this video, we're going to take a look at the ID3 algorithm. And in particular, we're going to explore this idea of what a best decision tree is. And we'll talk about how the ID3 algorithm defines best. It isn't necessarily always going to be the maximally optimal tree because it turns out that finding the optimal tree is too difficult for us to do. But we'll talk through the process of building this and start into the underlying ideas of information theory that guide the building of decision trees. So we'll start here. This is this decision tree that we've already seen in earlier videos. It's a typical look for a decision tree. We have questions which come from our attributes that are the interior nodes. The range of values of those attributes are turned into a discrete number of child subtrees, and then each subtree continues to ask questions as needed until it can assign a category for whatever remains. And we may have a few where we just are lacking data. There are some other things that can happen as well. We'll talk about that a little bit more when we talk about the ID3 algorithm. So we could choose to ask different questions in different orders, right? So here we chose color. What if we had put personality at the top? Would that have given us a better tree or a worse tree? What if we put fur type at the top? So we have all these decisions when we want to make a decision tree, and the most important one is what questions do we ask in what order to get the best possible solution. This tree right here for the data set we're dealing with is not the optimal decision tree. I'll tell you that up front. It's kind of middle of the road. So let's take a look really quickly at the data. This is the data set of good dogs, one of them. I have several versions of this toy data set. And you can see that we have dogs described by their attributes. Gray, medium, long hair, placid personality, that's a no. Gray, big, long hair, hyper personality, that's a no. This is not a particularly well balanced data set because you see we have a lot more no's than we have yeses. But what we're trying to figure out is what do the yeses all have in common? That's the pattern we want. That's what we want to capture with the decision tree. So from that, we might build this tree. We could also build other trees. So to give you a ridiculous example, suppose that I ask about personality type first, and then color, and then size, and then fur type. You can see this tree looks kind of ridiculously large because we're asking about every color at the same point, and we end up having to ask about all of the attributes because I carefully chose this to be maybe the worst decision tree for this particular data set that we might have. Now this looks a little over the top, but I'll say that in actuality, if you were to ask the questions in these order, it does simplify a little bit because the data set is so small. This is actually what you would get if you started with personality and then color. You really don't have to go that much further before you're going to bottom out and hit the limits of the data that we have. But in any case, we don't know that this is a particularly great decision tree. We would like to see what the optimal decision tree looks like. For this data set, the optimal decision tree looks like this. And it will generalize much better than the silly example, which was very, very specific to the examples in our particular data set. So if we ask about fur type, judging from the data, there are no long-haired yes dogs, so we can say that any dog with long hair is a no. And among the short dogs, the only ones that have a yes are the short-haired dogs, the only ones that have a yes are the big short-haired dogs. Medium or small dogs are all a no on that front. So this is the tree we would kind of like our algorithm to come up with because it's small and simple and it captures the important regularities in the data set. I can tell you I generated this data set with a program and these were the rules that I used. Anything that's a short-haired large dog is a yes, anything else is a no. So this is the best we're going to possibly do. Can we find the best tree? That's the question. Can we come up with an algorithm to find the best tree? We want a small tree in some sense But it's also a little bit unclear what we mean by smallest or best. There are ways that we could try to measure it. Like, we like the fact that a significant number of examples were eliminated in the very first question, so that the amount of data that we still had to ask questions about was relatively small. So it's not necessarily the shortest tree, the tree that has the least height, but it's the tree that's going to discriminate rapidly among the elements in the data set. More importantly, we want it to generalize, and that means looking even beyond the data that's in the data set to understand the larger space. So it's not entirely clear that we know what we want, but we can make some good guesses. And it has been proven that if you define what you mean by best tree, finding the best decision tree is an NP complete problem. It is intractable. We can't do it without exhaustively looking at every decision tree and assessing it according to whatever we've decided is our best, our definition of a best tree. So whatever we do, we want it to give us a good enough tree. That's almost kind of the way that machine learning algorithms work in general. We can't use something like a greedy algorithm or something that's guaranteed success. We really just have to do the best we can with the data that we have. So what we do to find the best tree is we want to put the most important attribute high in the tree. And the ID3 algorithm, which is one of the foundational algorithms that underlies many more complex algorithms that you might find in packages such as scikit-learn. ID3 uses ideas from information theory to help it decide what we mean by the most important attribute. So the fundamental idea for a lot of these decision tree builders is we're going to build the tree from the top down. We'll look at our data set. We will choose among the attributes that we have which one is the most important attribute. We're going to ask that first. So the first question is the most important attribute, and then we are dividing our data set into different parts based on the values of that attribute. So in this case, maybe there are 4 different values or 4 different sequences of values, depending on how your algorithm works. And what we've done is to generate 4 different versions of now the same problem. Why? Because, well, what we want to do over here is we want to build the best decision tree for the elements that have this value. That's just the original question, but on a smaller example. So this is a classic example where we want a recursive algorithm. So we're going to choose the best attribute. We're going to subdivide the data into sections based on their values according to that attribute. And then we will recursively build the best decision tree separately for each different subtree. And then that recursive process just plays out until they end up hitting leaves. All right, so the decision tree algorithm, as we're going to think about it, we are given cases or instances or examples. We have attributes that those cases have, and each attribute has some number of values that it takes on. And we're going to assume that we're going to have come into this algorithm a default value that should be assigned if all else fails. This varies depending on the algorithm and how you want to do it. You could start that off with an I don't know value. Or you could have a default value that is calculated from higher up in the tree of some sort. So the default value is there to help us if we get to a case, because this is a recursive algorithm. If we get to a case where when we call the algorithm, there actually are not any cases left. We've run out of data. We may have some attributes we haven't asked about yet, but we no longer have any cases. It's like those little pink boxes with the question marks from the diagram of a tree from earlier. If that's the case, we just need to stop. We need to make a leaf node for our tree, and we want to give that leaf node something as a default value. We could give it a value that means I don't know because I don't have any data. We could also give it the value that's represented as like the winning value from the parent node. From all of the data that we had, one level up in the tree, we just pick the most likely answer and we stick that in the tree. Those are the two alternatives that are most common for how you handle the default value. All right, so this is one of our base cases in our recursive algorithm. If we have no cases left, we're going to build a leaf. Okay, what if we do have cases left, but they all have the same target value? They all have the same category. Well, then we don't need to go any further. They all have the same category. We make a leaf node with that value in it. And we're done. So the search bottoms out at that point. The other thing that could happen is that we would have cases left, but we don't have any attributes left. What does that mean? That means that these examples all have the same values for all the attributes. We have asked about every attribute that there is, but they all have the same attributes, but they don't all have the same category, because I wouldn't get there if unless I have missed this case. So if you run out of attributes, it means that the examples, the cases you have, are inconsistent in their answers. You don't have all yeses, you don't have all nos, it's a mixture. And that means we don't have enough attributes to distinguish these cases from each other. So we make a leaf and we pick the majority of the ones that we have, or we have a special value we put in the tree that says, hey, I don't know quite what to do here. I don't have enough data to make a distinction, to decide. And here it's not the case that we don't have any cases. We just have cases that disagree about what the answer should be. All right, all of this that I've just gone over are basically the base situations when we're building a leaf and we don't need to do any more recursion. What I have down here at the bottom are basically the steps, the high-level steps of what we do if these cases don't pertain. So if we have lots of cases, they don't agree in value, and we still have attributes we haven't asked about, then we're going to do that recursive process, picking a node and then making branching into different subtrees and recursively solving the subtrees. And that's really what these three steps are. We want to pick the best attribute and make a node for the tree for it. We're going to split the cases we have left into subsets based on their values of that attributes. So that's like splitting the dogs into just brown dogs, just black dogs, just white dogs, just gray dogs, right? Splitting the data so that we have subsets that match the different attribute values for the attribute we've chosen. And then we're going to recursively build a tree for each subset. Okay. This is all of that written out in slightly more formal pseudocode. I'm providing this in another document, so I'm not really going to get into it here. I'll just note that examples here is what I was calling cases in the other place. Attributes, the default values are exactly the same thing. So if I have no examples left, then I make a leaf with the default value. If all examples have the same category, then I make a leaf with that. And if there are no attributes left, I make a leaf with the majority value. And then these just kind of play out like in pseudocode what it would look like to go through all of the different examples and recursively build a subtree. And so I will let you dig into that on your own or as we go through a more detailed example later. So we have this one big glaring place here, which is how do I decide what is the best attribute? I said before, it's based on information theory. Well, what exactly are we talking about? Specifically, we're talking about the notion of information as something quantifiable, so that we can look at a set of data and decide how much entropy it has. And we define entropy in information theory to be about how much uncertainty there is about the answer to the question. So if we're talking about an attribute, it would be like, if I ask about color, how uncertain am I that I'm going to get a particular answer? Like if all the dogs in the data set are black and I ask that question, I'm certain already that the answer is going to be they're all black. Whereas if they're all different colors, I'm more uncertain about the color of any particular one. So information theory has this notion of information as a quantifiable value, and of entropy as capturing how much variation there is in the information that we have. And then it also has this concept of gain that says, if I asked a question, how much information would I gain from that? Gain is what we use to decide which attributes are the best. I'm not going to go into the formulas for gain here. I'll do that in the next video. But just for now, gain is something you can take a collection of data and you can calculate the gain based on some pretty ugly formulas. And it's a number, right? So at the very top level in the dog example, if I calculated the gain for each of the attributes of the dog, we have color, size, fur type, and personality. You can see these are the gain values you would actually get for this particular data set. Color doesn't really tell us very much. We put that at the top of our initial tree, but it doesn't actually give us much gain. It lets us know that gray dogs are out, but it doesn't discriminate well, it doesn't help us very much with the rest of the dog categories. Fur type and personality are very similar. You get a certain amount from asking those, but size is really important. So we would pick size to be at the top of the tree. If we do that, and we then subdivide the data into small dogs, medium dogs, and large dogs, then we would look at each of those categories and we'd want to figure out say what the gain is there. We would be looking at one particular, well, I guess what happens with size is small and medium dogs are out, so it's all about the large dogs. Some large dogs are acceptable, some large dogs are not. So we would then, looking at just the large dogs, we would calculate the gain for the 3 remaining attributes. Color helps us somewhat, personality helps us somewhat, but the largest by far is fur type. So that would be our second level question that we would ask. And it turns out that when you do that, it divides up the data and you're done. So that would give us this as our best tree. It's just flipped around those 2 questions. It's still equally optimal, maybe more so, because it's actually getting rid of 2/3 of the data potentially with one question, and then one more question allows us to divide the rest of the data. So this is pretty good. This is what we would hope to get from ID3 given this data set. All right, so this is a high-level view of what the ID3 algorithm is all about. What we'll be doing next is digging into the information theory a little bit, looking at how we calculate information, entropy, gain. There are a couple of other pieces of that we have to do. And we'll be looking at slightly different versions of the formulas than what you might see in the textbook, because it'll be easier when we want to actually implement ID3, which is on your list of things to do. All right, I will see you very soon.